Hi everyone, I've recently been messing about with creating little procedural planets, and there's still loads of things that need to be improved, but by far the most upsetting thing is how the sky is pitch black even in the middle of the day. So to fix that, in this video I'm going to be attempting to create some atmosphere. My first step is going to be to write a post-processing shader that'll be responsible for drawing the atmosphere around our little planets. So this here is the fragment program of that shader, which will be run for every pixel on the screen. So for example, if I get the current pixel color and return 1 minus that, we'll end up with this. That's not terribly helpful though. Instead, I want to draw essentially a bubble, so we'll need to figure out where the view from the camera intersects with a sphere around the planet. Happily, I already have this bit of code from the simple ocean shader last video, and that'll tell us how far the view ray has to travel to reach the surface of the sphere, and also how far it travels through the sphere. To complicate matters a bit, if we're looking at the planet, then the distance through the sphere should be cut short by the planet's surface. So let's dive back into the shader, and I'll start by getting the origin and direction of the view ray for the current pixel, which we can then give to that ray sphere function to find the distance to and through the atmosphere. I've long since lost any faith in the code I write, so to quickly check that this is doing what I hope it's doing, I'll return the distance through the sphere divided by the sphere's diameter, and actually that does look about right. We still need to account for the planet's surface though, so we can sample from the camera's depth texture, which will just tell us how far away whatever was drawn to this pixel is. We can then correct the distance through the atmosphere like so. This is the result now, but annoyingly you might notice that the ocean isn't being accounted for, which is because it's actually a post-processing effect as well, and not included in that depth texture. So I'll need to quickly go back yet again and just calculate the distance to the ocean sphere over here, and then the distance to the planet's surface is whichever is smallest between the scene depth value and the distance to the ocean. Just to liven things up a bit, I'll multiply the output by the view ray's direction, with x, y, and z being interpreted as red, green, and blue, and that'll give us this groovy result. So, we've got our little bubble, but to make this actually look like an atmosphere is clearly going to take some work. I do have some idea how to approach it though, because a little while back I experimented with clouds, and the basic idea there was to represent the density of water droplets by mixing layers of noise, and then approximate how light might be scattered as it travels through that space. The scattering of light is also what makes the atmosphere visible, so I'll be able to draw on what I learned from these great resources during my research for the clouds. But I'm also going to be using accurate atmospheric scattering by Sean O'Neill as my guide for this project, because it looks like a really nice breakdown of how to actually compute these intimidating looking scattering equations. So an atmosphere is made up of loads of tiny little molecules like nitrogen and oxygen in the case of Earth, and these will be quite tightly packed together close to the surface, but as we go higher and higher, gravity gets weaker and there's less gas pushing down from above, and so the little molecules will be spaced further and further apart, and at a certain altitude, for practical purposes, we'll say that's the end of the atmosphere. Now, light from the sun enters the atmosphere, and its interactions with the gas molecules cause it to scatter about. The type of scattering we have here is called Rayleigh scattering, which happens when the size of whatever's doing the scattering, like our gas molecules, is a lot smaller than the wavelength of the light. In this case, when the light interacts with the molecule, it will mostly be scattered forwards and backwards, and less so in a perpendicular direction, giving us this pleasant peanut pattern. Happily, unless you despise blue skies and sunsets, the amount of scattering is dependent on the wavelength of the light, with violet light for instance being scattered about 10 times as much as red light. Intuitively, I guess this makes sense if you think how shorter wavelengths will have more opportunities to interact with stuff, but I'm not sure if that's how it actually works in the confusing quantum-y realm of light. Anyway, this is in contrast to Mie scattering, which occurs with things that are roughly the same size or larger than the wavelength of light, such as dust particles or water droplets in clouds. In this case, the light is predominantly scattered forwards, and all wavelengths are affected pretty much equally, which is why clouds appear greyish-white, for example. Again, I guess it makes sense that when the things you're interacting with are big, having a shorter wavelength doesn't really help you meet more of them. For today though, I'm just going to focus on Rayleigh scattering. So as we saw, violet light scatters the most, so it'll be coming from pretty much every direction, meaning wherever you look it's going to be entering your eyes, making the sky that distinctive violet colour we all know and love. Okay, after a little research, apparently the sun doesn't produce that much violet light, and our eyes are also less sensitive to it, so blue predominates. Green light doesn't scatter as much as blue does, and red light even less so you won't see much of them unless you're looking directly at the sun. However, if our viewer is all the way over here, then it's an extra long journey through the atmosphere, so almost all of the blue light is going to get scattered away before reaching the viewer. Most of the green light will be scattered away too, leaving primarily the red light, which will scatter a bit as well, giving us a beautiful fiery sunrise or sunset. Unfortunately, if we were to try simulate all these little interactions, it would take hours and hours to render a single frame, which wouldn't make for the most exhilarating gaming experience. So we're going to need to resort to some crude statistical approximations. Let's get back to the code editor, and I'm going to make a little function called calculateLight, which will take in an origin, direction, and length to describe the view ray of the camera through the atmosphere for the current pixel. The only way for that pixel to be illuminated, at least in our simplified model, is if light travels from the sun and gets scattered into the path of the view ray, which I'll refer to as inscattering. Now, this could happen anywhere along the view ray, but in order to calculate it, we'll need to pick a finite number of points, with more obviously being better for quality but worse for speed. So in the code, I'll set the first inscatter point to be at the ray origin, and then I'll run a loop for the number of points we want, and move the point along the view ray by the step size, which is just the distance between the points, and we can calculate that like so. I'll then also make a variable to keep track of the total amount of light scattered in across all these points. So now the question is, how much light from the sun is actually reaching each of these inscatter points? Because some of it is going to scatter away before it gets there, and the amount that scatters away depends on the average density of the atmosphere along this ray where the light is travelling, or as it seems to be called in fancy physics terms, the optical depth. So in the code, let's first figure out the length of the sun ray, which we can do using the ray sphere function from earlier. Then, to calculate the optical depth, I'll use my favourite programming trick, which is calling a function that doesn't exist and worrying about it later. Now, the proportion of light that makes it all the way to the inscatter point, I'll call the transmittance. I'm trying to learn the right terminology, but I'm not sure if I'm succeeding. In any case, if we make a little graph like this, when the optical depth is 0, the transmittance will be 1 because all the light will make it to its destination. But as the optical depth increases, more and more light will get scattered away, and so we'll see an exponential fall-off in the amount of transmitted light. The actual function being graphed here is transmittance is equal to e to the power of negative optical depth. In the code, we can write this using the built-in exponential function, which just raises e to the given power. So now that we have an idea of how much light will reach the point, the next question is how much of that will be scattered towards the camera? Well, one thing this depends on is this angle here, and this is where we could use that p-naught function from earlier, which would make less light scatter at 90 degrees, making the sky a bit darker there. I'm going to leave it out for now though, because the most important factor is the density at the scatter point. So in the code, I'll just make up a new function to sample density at a single point, and then the greater that density, the more light will be scattered, so we can increase the inscattered light by that, multiplied by the transmittance and the step size. One more thing we need to take into account is that as this inscattered light travels towards the camera, some of it will be scattered away there as well. So in the code, I'll figure out the optical depth from the inscatter point to the camera, and then update the transmittance to account for that. This calculation can actually be simplified to just use a single exponential function, simply by adding the two values together. It amounts to the same thing. Anyway, we can now return the amount of light that makes it all the way to the camera, and our function is complete. We still have to implement those two functions I pulled from thin air though, so let's start with the density at a single point. Remember that the atmosphere is most dense close to the surface and becomes exponentially less dense the higher up we go. So in the code, I'll calculate the height above the surface like so, and then I'll scale it to be 0 at the surface and 1 at the outer shell of the atmosphere, just to make it easier to work with. Now we can use that same exponential function from before, and I'll multiply the height in there by some density fall-off variable, so that we can control the shape of this fall-off curve like so. Now it's a little upsetting to me that the density can be above 0 past the atmosphere shell, so I'm going to do something a little gross, and just multiply this by 1 minus the scaled height. This will force the density to be 0 at the atmosphere shell, so we can use whatever fall-off value we like, although negative values would be a little weird. We can finish off this function by just returning the result, and then let's move on to the optical depth function. Remember, this is essentially calculating the average atmospheric density along a ray. So if this here is our ray, the way we'll estimate the value is simply by breaking it down into a number of points, sampling the density at each of those using the function we just wrote, and then adding them together and multiplying by the step size. The code for this is not terribly interesting, so let's just rush through it quickly. We set the sample point to start at the ray origin, then calculate the step size and initialize the optical depth to 0. Next we loop for the number of points we want, calculate the density at the current sample point, add that to the optical depth multiplied by the step size, move the sample point along the ray, and once the loop is complete, return the result. With that done, we can at last get back to the fragment program from earlier, and in here I'll check if we're looking through the atmosphere, and if so, we'll want to find the first point along the view ray that's inside the atmosphere. And then we can call the calculate light function, passing in that point, along with the ray direction and the distance through the atmosphere. I'll then output the original color blended with the light, and if we're not looking through the atmosphere, then just the original color. Perhaps one day I'll write a piece of code that runs perfectly the first time. But today was not that day. I had to go back and fix some syntax errors, after which the pink screen was gone, but the atmosphere was way too intense. No problem, I thought, that's what the density fall-off is for, but that just made things weird. I was curious about the noisy region behind the planet, and so I tried zooming in on it. I'm not sure why these patterns occur in the noise, but it seems to be caused by the ray sphere function struggling with precision issues when the given point is right on the surface of the sphere. So in the code, if I have some tiny value and add it to the starting point and subtract it from the ray length, then the noise disappears. Of course, the strange cylinder behind my planet is not exactly welcome either, and I eventually tracked that down to a little missing minus sign right over here. With that fixed, we're now left with a little misty ball around the planet. I'm excited to play with the settings a bit. I want to see what this looks like with a negative density fall-off. Kind of like a force field around the planet, I guess. We can also play with the scale of the atmosphere, and then lastly I have a tiny sun which I can rotate around just to see how that affects the lighting. This is quite boring without color actually, so let's try fix that. We need to form our image out of red, green and blue, so let's get a rough idea of those wavelengths. Red is around 700 nanometers, green maybe about 530, and blue let's say 440. Remember also that the amount of scattering is inversely proportional to the fourth power of the wavelength. So I have this atmosphere settings script which is responsible for sending settings over to the shader, and in here I'll add a variable to store those wavelengths along with a scattering strength variable. Now we can say that the scattering strength of red light is equal to 1 over the wavelength to the power 4 multiplied by the scattering strength, and I'll do the same for green and blue. Now I don't want these values to be ridiculously small because that's annoying to work with, so I'll actually change it from 1 over the wavelength to maybe 400 over the wavelength, just something that'll bring the results somewhere not too far from 1. We can then send that data over to the shader, and let's hop over there ourselves to actually do something with it. So over here we have our transmittance variable, and I'll make this a float 3 so that it can hold different values for red, green and blue light. And then I'll multiply the optical depths inside the exponential function by the scattering coefficients. If we look at a graph of the transmittance now, with the scattering strength set to 0, all the light will be transmitted. But as the strength increases, you can see the different wavelengths separating based on those scattering coefficients we calculated. And note that red light is transmitted the most and blue the least, so the math seems to check out. The scattering coefficients also of course affect how much light gets scattered in towards the camera, so we'll need to multiply over here as well. This means the in-scattered light variable will need to be a float 3, and so the function will need to return a float 3 as well. I'm also going to make it take in the original color so that we can blend that with the in-scattered light here. I'm not actually sure how to properly do this, so I'm just going to use a crude approach for now, which is making some of the original color get scattered away on its path to the camera, and just adding the in-scattered light on top of that. We'll need to quickly go back to the fragment program to just update it to work with this new setup, but with that done, we're ready for the moment of truth. This is a bit underwhelming, so I'm going to crank up the scattering strength and hope for the best. Okay, maybe the angels are overselling it a bit, but I do think it looks quite nice. I love messing with settings, so I'm going to again play with the atmosphere scale. That looks kind of weird, we'll pretend we didn't see that. And I'll also try changing the density falloff, but most enticing are the new wavelength settings, so let's try tempering with those. I like this pinkish purple one a lot, and you can see around the edge the green sunset turning now into a pale blue. Let's try something a little more dramatic and really split the color bands apart, which gives us this wild looking rainbow atmosphere. That's a lot of fun to mess with, but I'm going to set these back to some more reasonable values for now, and let's have a look at this from some other angles. I'll also zoom out a bit, and just for comparison, I'll switch the atmosphere off for a moment. It suddenly looks so hideous without it. Ah, that's better. Now, some of you might be wondering how this shader is in terms of performance, and the short answer is not great. The longer answer is that of course it depends on the number of in-scattering and optical depth points we choose, so let's take a closer look at those. With just one in-scatter point, the result is nonsense. 2 and 3 are pretty bad as well, but after that it seems to converge pretty quickly. And this is the same with the number of optical depth points, so around 10 for both seems to be reasonable, at least for this atmosphere's settings. Even that's a bit slow, but thankfully that write-up I showed earlier has a section on optimization, and one of the first things described is pre-computing the optical depths for all rays through the atmosphere, and storing that in a little 2D texture. This takes that entire loop that we're having to run for every in-scatter point, and just replaces it with a texture lookup. That sped things up immensely, with the minor trade-off of completely ruining everything. I got it working in the end though, and moved on to stars, which I completely messed up as well, in many different ways. What I ended up with is a bit dubious, but I'll improve it later, hopefully. It's essentially just a mesh of a bunch of circles, and I can control their size and number and color and so on, and then they're drawn with a little shader which looks up the color of the screen where the star is, and based on how bright that is, fades the star out. This means that during daytime the stars won't be visible, but as the sun goes down they'll gradually come out to play. Now, you might notice some ugly color banding going on in the darker areas of the atmosphere, and this is something I was able to combat a bit by using blue noise to jitter the in-scattered light by a tiny amount. This works pretty well in the game, but unfortunately the video capture still suffers from these distressing artifacts. Nevertheless, now that our little atmosphere is in place, let's go explore the planet. far off in the distance we can spy the planet Cyclops with its purplish atmosphere, so let's head over there next to take a closer look. So that's essentially all there is to see for now. I think the atmospheres have improved the look of the planet substantially, so I'm happy with it as a starting point. But I'm also very curious to read through some more recent works on atmospheric rendering, because the write-up I've been following dates all the way back to 2005, so I'm sure there's been plenty of new ideas and approaches since then to experiment with. I'd also love to add some fluffy little clouds and varying weather conditions to the planets, not to mention plants and animals. Plenty to keep me busy for sure. Anyway, that's all I have for now, so I hope you've enjoyed this video, and until next time, cheers.